That was great. Now, I don't know if you're trying to talk, but I cannot hear your microphone. Jessica, do you have your mic on? We're not able to hear you yet. Can you double check your microphone, Jess? I don't know if there's maybe a way to turn your volume up on the mic. Looks like it's on its lowest setting.
Oh, here we go.
Here we go. All right.
Okay, can you hear me now?
We do. Thank you for your video.
Okay. So this is the project area, so New York. I'm just going to zoom in. And yeah, I was just trying to demonstrate with that previous video, cascading dam breach and what that looks like. And so here, this is the area, the Erie Canal, starting at the Crescent Dam, which is here. And then it comes through, these are two guard gates, which for the analysis were assumed to be closed, as well as all the locks were closed. And so this is lock E6 here and the dam. The flow would come through this way to the spillway here, and then proceed in this direction to E4 and over this spillway and down this windy bend under this bridge, and then through this, out through the lateral culvert there, and then continuing this way. This is E3. I can zoom in a little bit so you can see that's a spillway. There's a, hard to see, but there's a pedestrian bridge over top. That's lock E3. There's a railroad bridge. That's the 9th Street Bridge. This is the Champlain Canal that's running perpendicular to the Erie Canal. This is a gate here. And this part is interesting. So this picture was actually taken down here. This is E2. It's really just sheet piling, or basically a sheet of metal. So that's what that area looks like. So basically, you have supercritical flow in that area, and then a bridge here and a bridge there, and this is the Hudson River. And there's a stream gauge not too far from the confluence there. There's also one downstream of the Crescent Dam. And I just want to jump really quick into the HEC-RAS mapper so you can get an idea of the topography of the area. So you can see that there's a pretty big difference, a change in elevation, 180 to 30 in the model. And the one thing I just wanted to point out is this area is very flat, pretty much all the same elevation, which adds to the complexity. And so the objective ended up just being wanting to look at breaches from each of those individual dams, and which then morphed into a cascading dam breach analysis. And so I wanted to kind of get your opinion after seeing the case study area. What would you do? And so this is the polls. So I think it's one at a time. They should come up.
The first one should be up now.
Okay. Are the questions on the screen?
I see them. I'm not able to answer them because I'm an organizer.
Okay. I'll just read, so we'll just give about maybe 20 seconds to answer each one. So the first one is, what model would you use to perform this analysis for this case, assuming no restrictions on what model could be used? And there's an other option, because I know some people would want to, you know, put some canals and dams together in the lab and see what it does in there. So just kind of wanting some input on that.
And Jessica, there are responses coming in.
Okay.
Do you see a polls thing on your dashboard at all?
I see, like, there's a little red thing that says poll open. So can we close that one and bring up the next one now?
Do you want the responses? It looks like people are still responding to your first question.
Okay. Okay. We can wait then a little bit.
Okay, so for your first response, it looks like 67% selected the first HEC-RAS option. 22% are saying flow 2D or flow 3D. And then 11% have selected other.
Okay.
All right, so I'm going to move on to the next one.
Okay.
Okay,
so this one, what approach would you use to perform a cascading dam breach flood inundation analysis for this area? Just 1D, 1D with 1D, 2D connections, just 2D or other?
Okay, so you got various responses here. So the most popular is just 2D, 56%. Then 1D with 1D, 2D connections, so option 2. And then split on third place at 10% for either just 1D or other.
Okay, interesting.
Okay.
And then the last question. Okay, so this one, C should be, I'm just going to say that, it should be 50 feet. Something happened in the email, the 0 got deleted, but C is 50 feet. So for this case with 1D modeling in HEC-RAS, how would you space the cross sections, not including spacing around structures? 15 feet, 25 feet, 50 feet, or variable spacing everywhere?
Okay, it looks like a majority of respondents have selected various spacing everywhere, that's 78%, and then 25 feet and 50 feet are tied at 11%.
Okay, awesome.
Right.
Okay.
Now it should go to your screen.
All right. Okay, so I picked HEC-RAS, and mainly because of agency client preference, went with 1D with some 2D areas, kind of working up to 2D. One of the concerns was modeling the bridges in 2D and making sure that they were accounted for and what the impacts to them were. And so just kind of some challenges with HEC-RAS. So HEC-RAS, this kind of is representative of HEC-RAS in steady state. This is HEC-RAS in unsteady state. So the more complexity you add to it, the more unstable it gets. And that's what I mean by complexity. HEC-RAS is really picky. It likes things to be a certain way. And so how do you deal with that? So I think the main important thing is it's a multi-objective model in terms of you want to look at the dam breaches being the main objective, but then you also want to understand what's maybe going on at the bridges, the impact that they have, the sensitivity related to that, to make sure that you're accounting for all of the different areas and their impact as well. And so how do you deal with this situation? And one of the ways is HTAB parameters for a 1D system. I believe now HEC-RAS lets you use 500, but the more you use, the longer the model takes to compute. Another helpful tip is using an iterative approach for complex boundary conditions. So for downstream, starting with a normal depth, getting a stage hydrograph from that, adding your depth that you want to use for whatever conditions to that, and then inputting that into the model is one way to handle it. Internal boundary tables for bridges. Use realistic flows when you're putting those in. That really helps the model to converge more easily. Ineffective flow areas, if they reduce complexity, they're helpful. If they make it more complex, not so much. And then cross-section spacing for inline structures. Downstream of an inline structure for 1D, don't put it too close, it doesn't work so well. So 50 to 100 feet for a dam break. Sometimes it likes levees, sometimes it likes ineffective flow areas, sometimes it doesn't like either one. And then one of the issues with 1D, one of the main issues is, what I call it, is it just draws a line across. So this shows where the flow comes over from the Champlain Canal. Some of it continues down into that supercritical area, and it's computing flow in here, and then basically it is computing divided flow, but it's drawing a line straight across. And so this is super conservative. Realistically, that's not necessarily how the extent of the flow or how deep it would necessarily be. And or it could be much deeper depending on how much water is coming over from the canal there. The other issue with 1D is making sure you're accounting for correct storage of dams. So making sure that you look at the volume that HEC-RAS is counting and make sure that that's what the actual storage is for your dam or reservoir. So with 1D, 2D areas, one issue is 2D areas and HEC-RAS don't really, in this case, they're fine to start out dry, but if you wet them and then dry them, there's an issue. So with low flows, it can be problematic. The other issue I found is trying to put 1 to 2D areas on opposing sides of the reach. There seem to be some flow balance issues. As you can see, these are the lateral structures, and the table on the top here, you can see the values aren't very realistic at all. The bottom one was better. So one way to handle that would be to put in one side and then model the other side separately without the 2D area on the other side to kind of get what the maximum extents would be. So this is the cascading breach. So you should be able to see the floodway in a few seconds, the flood wave in a few seconds. It starts up here and works its way down. And the timings were set to have each one breach when the wave from the previous breach reached that point. Oh, there we go. Okay. So this is the results of this particular model with the 2D flow area here. And then here again, like I said, I'm a little bit over predicting what's going on there. So one way to handle that would be with adding a 2D area here, which I did, and I try to recompute the results, and it just was taking way too long, which is one issue, like talking like maybe a couple of hours to compute this. But if you wanted to get more realistic results, the other ones were conservative and useful. But this would give you a little bit more realistic depiction of where the extents of the floodplain are, or the dam breach flood wave inundation area. This is just a close-up of that area. So I don't really have a whole lot of time to talk about the hydrology, so I'm just gonna skip over this. But just to say, it was based on the half PMF, and just one tip to get the model to run. I started with a preliminary hydrograph, so calculating what the peak flow would be expected to be and keeping that peak flow at a plateau and just building a hydrograph up to that point, getting the model to balance and be stable and run, and then putting in what the hydrograph would actually be with respect to the volume. And so this is also some ideas I had for a different alternative using unit hydrograph theory and the gauges, and along with historic rainfall data for future research, and linear optimization to be able to come up with the volume of the PMF based off of, which would be based off of historic storm data in that specific area. So any questions or comments? And if you have any comments or feedback or suggestions, I'd love to hear it. Please email me and let me know. I'm really interested in learning other ideas and approaches and recommendations you might have.
Great, thank you, Jessica. So y'all can either raise your hand and I'll turn your microphone on, or you can enter your questions into the chat queue.